So this lecture is basically is something relating to the work one course, and I have to read on the lecture in the work one, and I summing up them together and then represent it in easier way to understand. Because I work with you most of the time, Chen, so I'm not sure about another participants. Do they have any more knowledge or not? But based on what I understand about you, so I make the lectures kind of stick to that path.
Yeah,
And
sure.
yeah. Okay. So I get two main part of the lecture today is about time complexity and recursion. And you already know that the big O notation is something um, mm, be generated to describe how much time the program or the algorithm will take by a during the execution. And and you can think that big O notation is taking the input. It could be a single variable, it could be the array, it could be the string, or it can be JSON, or it can be a large, huge data set as you are working with. Big O is like you not understand kind of function, and the return of the function, I mean function equals fx, I mean fn, and you can see n, and the time consuming will be displayed, will be computed by using the big O notation. Actually, we just kind of quantify, quantify the time by looking at the big O notation. Somehow we, um, by using some given time, how to say, time estimating function that we already discussed in last two lectures about in Python, you can see the real time execution of the function. But by just looking at the big O notation, we can we can estimate how much time the program or the function will take by given data input. So over here I have here a 1, 2, 3, 4, 5, 6 kind of on. You see, but today we will go through three of them. You see, this is one kind of on, or O1. I'm sorry. This is O log n. This is on. Jen, I think this is a little bit difficult, but about the basic mathematics, you see the on is the linear function, right?
Yes,
On is,
yes.
yeah,
Yesterday I
linear
got
function.
the yes. Yesterday I covered the logarithm already, so I understand the math. So don't worry.
Yeah, nice. We have the log n here is the logarithm function. O1 actually similar to O2, similar to O, sorry, because I'm writing by my mouse, OX, which is a given constant number. You can see over here, right? Um, by any given data input, you want 1, 2, 3, 4,000, 3 billion or something, the time consuming will be the same. You see that? But for example, for the linear time complexity over here, the time consuming by execution the function will be linear, to the data input. And we have the higher order of O like this, like this. Okay, so one thing to notice at the moment, right at the moment, is depending on how much data input. For example, I will I will draw the line, say, I will draw the line like this. Depending on how much data input, the one we have many way to write the function to write the program, right? But the complexity, you see, is somehow describe the let me think about at by the number of data input over here. This this function, this program take less time than this program, right? So it will be cover somewhere here, and this program will take less time than this program. Similarly, for if we have any specific data input over here, right? This this function, which have the complexity on, will take more time than this function, and definitely take more time than this function. So summing up that depending on the data input, each function will have the specific time for it. But when we consider the data go to infinitive, we have to look at the infinitive set of data, so we can choose the right function for choose the right algorithm for a specific case. But for smaller data input over here, we don't need to overkill it, right? We don't need to choose a function that have more complexity than the other. So you get my point?
Yes, yes, I think I understand.
Yeah. Okay. So just a short introduction about the ON, and I will dive it into the most simple one is the O1. So let's take a simple program like this. We have the function, like the function summing over here. So this kind of, I like a stupid function, right? Because this function does nothing but just define a variable equals 0 and return total return 0, right? Doesn't matter you input what a here, what array is, it will always return 0, right? So this one take a time t1. You can measure it by using the Python helper function, and this one take t2. Okay, and when I call the program summing a, this one is executing one time, mean this kind of this line of code is called one time. This line of code is called one time also, right? So we have the total time for executing two lines of code is 1, which means one time, multiplied by t1 over here, plus 1 here mean one time, multiplied by t2. So far so good?
Yes, it's all right.
Okay. So we will have the constant. T must be the constant because they are on a constant. So we call this the O1 complex because whatever you enter the A over here, whatever you enter the array, it will always return the same time consuming, right?
Yes.
Okay. Okay. So let me in other words, this is the O1 complex, and this one also similar to O2, similar to O X, which X is a constant given number. X is given number. Okay. This is the reason why I say ON equal to O1, O1 equal to O2 equal to O3, because you see this one very similar to the previous example over here, but I have one more line right next to first line. Like I say, this is like a stupid function because it doesn't do anything, right? Just like you repeat it again and it have no means. But just my example in how we can describe the O2. Like again, oh, I'm sorry, this is 2 times. This line of code consuming 2 times multiplied by T1. This line of code consume 1 time multiplied by 2 1 time because it is called 1 time when you invoke the summing over here, right? So we have the T total time execution is 2 multiplied by T1 plus 1 multiplied by T2. So far so good.
A moment to double check on the code. Yes, I think. Sorry, I'm lost on the last one. Like this summing function O2 is complex. Like I'm lost on the red thing that you wrote. Like the other slide. Cái slide sau ấy, cái slide sau ấy. Chị không hiểu là cái O1 bằng O2 là
cái này không phải là bằng mà là mình ký hiệu này là tương đương đó chị. Ký hiệu này, nhưng mà tại vì em tìm ký hiệu này nên là em dùng cái này. Tương đương.
Mà sao O1 tương đương O2?
Smith có hiểu tiếng Việt không chị? Mình nói tiếng Việt cho nó
dễ. Hiểu rành lắm.
Yeah, just a moment, shoot.
Yeah, we're talking about you.
Yeah, I know. I could understand some of what you were saying.
Yeah, thank you. Để mà hiểu rõ cái việc là O1 tại sao mà nó tương đương với O2 thì phải có một cái định nghĩa về cái phương trình toán về cái fx bằng g của x này kia, nhưng mà cái đó nó hơi khó hiểu. Thì em nghĩ thế này nè, là tạm thời mình chấp nhận cái việc là O1 nó tương đương O2. Ý em nói lúc nãy là cái O mà ở trong đó là số x á, mà miễn sao cái x này là số mà mình biết trước, ví dụ như 1, 2, 3, 4, 5, 6 hoặc 1000 gì đó, thì nó sẽ tương đương nhau, cái độ phức tạp nó tương đương nhau.
Ok, cái độ phức tạp chị hiểu rồi. Ok. Yeah,
thì bây giờ mình thống nhất với nhau luôn là mình gọi O gì đó, tức là độ phức tạp của nó.
Ok.
Yeah.
Yes.
Quay lại chút xíu là chỗ này. Ví dụ như chỗ này là O1. Em cũng có ghi ở đây là O tương đương với O2 với O3, miễn sao cái số trong đây là số mà không phải là ẩn số giống như là n hoặc là log n hoặc là n bình kia.
Okay. Yes.
Yeah.
Oh, okay. So we are talking about the line of graph, and as long as it's the same form, that is same complexity. Okay.
Summing function mean this one. Summing function. So the complexity of summing function is O1. Tương tự như vậy thì cái summing bên đây nè nó cũng có độ phức tạp là O2, O2 thì lại tương đương với O1, cho nên là nó cũng có độ phức tạp O1 luôn.
Ok, chị ơi, chị hiểu.
Dạ rồi. Chút nữa sẽ có cái ví dụ ON thì em lúc đó em sẽ nói kỹ hơn.
Ok.
Thì làm sao mình biết được rằng cái độ phức tạp của nó là O gì, mà có cái em chấm ở đây, tức là mình không biết mình điền cái gì vô, có thể là hoặc là 1, có thể là n bình, vân vân. Thì cái chỗ này nè nó được định nghĩa là cái degree, tức là cái mũ, cái độ gì lớn nhất cái term mà trong cái hàm số mà định nghĩa cái độ phức tạp về thời gian. Tạm thời mình bỏ qua cái này đi, nhưng mà lấy cái này làm ví dụ nè.
Ok.
Lấy cái này làm ví dụ, em có một cái hàm là ax mũ 8 cộng bx bình cộng c, thì cái này là một cái term của nó, cái này là một cái term nữa, và cái này là một cái term nữa. Thì cái ax mũ 8 này á, do là nó mũ 8 luôn, a nhân cho x mũ 8 nha, cho nên là cái degree, cái tiếng Việt là gì thì em quên mất rồi, nhưng mà cái độ của nó lớn hơn. Dạ. Bậc của phương trình. Ví dụ như là a x bình cộng b x cộng c thì tức là phương trình bậc 2. Còn cái này là phương trình bậc 8. Thì tương tự như vậy, mình đổi x thành con số n đi, mà n ở đây á, tức là cái số lần lặp đi lặp lại của một cái dòng code nào đó, hoặc là một nhóm dòng code nào đó, thì mình sẽ có là ax mũ 8, em viết xuống đây luôn nha, tương đương xuống đây nha. Thì an mũ 8 cộng bn bình cộng c, thì cái phần mà điền vô trong đây nè, cái chấm này nè, chính là cái con số mà n mũ 8 ở đây.
Hang on. Let me have a moment. So the highest degree of term in the function could be defined. Okay. Vậy là cái mũ là cái define cái function, cái complexity.
Dạ đúng, nhưng mà không phải lúc nào cũng là mũ. Có khi nó sẽ là log, có khi nó sẽ là n nhân log, có khi nó là 1.
Okay.
Thì chị nắm được khoảng này không?
Highest degree in term function. Nhưng mà log với lại mũ là nó cũng giống nhau đúng không?
Cái hàm log với hàm mũ thì nó khác nhau. Quay lại cái này một chút, là chị dần thấy cái hàm log nè, hàm màu đỏ nè. Cái hàm log của n thì nó sẽ đi lên, theo hướng này nhanh, nhưng mà khi mà t nó tiến tới vô cùng á, cái lúc mà đi về hướng vô cùng á, thì nó sẽ đi lại như thế này. Còn cái hàm mũ á, thì nó sẽ đi, ban đầu xuất phát khá là chậm, nhưng mà khi mà càng về sau nó càng nhanh lên.
Okay. Yeah. We just talk about like the complexity of log and square and power. Okay. Yeah, okay.
Em tới đây thì em ví dụ em nói lại cái việc mà mình xác định cái data input á, thì ví dụ chị thấy cùng một cái lượng data như nhau, nhưng tại cái lượng data này thì cái hàm log này á, nó mất khoảng thời gian nhiêu đây. Nhưng mà cái hàm này nè, thật ra cái hàm ON mũ 3 này nó em lấy cái hàm ON bình này cho dễ. O n bình thì nó lại mất khoảng thời gian ít hơn. Nhưng mà với cái lượng data này đi, với lượng data này đi thì cái lượng O n bình này nè nó mất cái thời gian nhiều hơn. Còn cái O log n thì nó mất khoảng thời gian ít hơn. Ý tưởng á, là mình phải chọn cái phương trình của mình sao cho phù hợp với cái lượng data input. Ví dụ như cái lượng data input là 100 mà cái thuật toán này nó mất thời gian là t thôi, nhưng mà thuật toán kia mất thời gian 3t, thì mình phải chọn cái mà nó ít thời gian hơn, nhưng mà ở một cái điểm bên đây input khác á, cái chỗ mà lượng data lớn hơn á, ngược lại.
Okay. Okay, I'm good. Let's switch back to English. I think we mix here. Yeah. So I think I'm good with this slide.
Yeah. Okay. Nice. Good to hear that. So you still go with this one, right?
Yeah, I'm good with this one. So basically, normally the complexity will be determined by either log or power or the step function, right? Like things that can like take a lot of steps in the function will be the major drive for the big O, right?
Yeah. Exactly.
Okay. Yeah, I think I'm
okay. All right. So I go to the next slide.
Yes.
Okay. Here is an example of ON. So we also have the summing function over here, but we have something more intelligent, smarter than the stupid one in the previous example, right? This one will take T1, we already know. This one will take T2, we already know, and the line over here will take the time T3. Is it my like assumption, right? Do you have any question at this example? I mean so far. I guess that you may have a question that why this one I didn't write anything about this slide, right? How much time does it take? Right? Because we have the 4 iterations. Yeah. So how do you think? What do you think about this slide?
Sorry, like what do you mean? Like are you trying to find the ON for this one, the big O for this one, or?
No, I am asking that, are you curious that why I didn't write any time consuming for this line of code?
Oh, it's just the elements, so there's no computation, right?
Yeah, elements.
Yeah, it's just like a for loop, so there is not any element. It's just a reasoning, like a condition. So there is no computation.
Exactly. Nice. Okay. So you have no yeah, exactly. That's good. And we can do the same thing like previous example. This one take one time, right? We call it one time. This one take one time also, right here. And this one is executed n times, which n is the size of the array. I mean, the list or the array are the same, right? So we have the the total time execution is 1 multiplied by T2 plus 1 multiplied by T2, T1, I'm sorry, plus n multiplied by T3. So can you guess or can you use the previous formula to describe the complexity of this algorithm? I mean, based on this explanation about whatever, can you use this one to figure out this C the ON?
Is the ON the power 2, right?
No, this is ON.
Oh, okay.
Yeah. My question is, how do you know this is ON? And by just looking at my explanation in the previous slide, in this one, and the time here, so you figure out this is the ON. I mean, how can you do it?
I thought like it would be ON power 2 because for each element there is another element, so it would be like n power 2.
Which element of element are you mentioning?
It's the for loop, so for each element there is another step to do with that element. Oh wait, for loop the for doesn't count. Okay, I got it. Yeah. Okay, I think I got it. Yeah, I think it's ON. Okay, I'm clear.
Yes, but actually my question is here. How can we transfer the t function here into the result of ON by using the previous knowledge? So we get the O something is based on the function, it on the time function, and we have the time function over here, right? So let me write it in the easier way to see. Sorry again, because the mouse I don't have the pen for. I think you could. Any we can.
Maybe you can open a Word, a document, or like, yeah, and then.
Yeah. Okay. Let me write. Yes. Let me write directly to here. So we got T equal T1 like I just want to rewrite the time function, right? Multiplied by T2 plus T1 plus T2. Okay. So please tell me what is the highest order in highest degree in this function?
Oh, it's just 1, right?
Yes, exactly. Exactly. You see n, right? We have like we have here in the previous example, we have a n over 8 and n to the 8, and we have n to the 8 complex. And in this example, we have just n. So this is on.
Yes, I think I'm clear on this.
Okay. Okay. So how about you, Smith? Smith, are you there?
Yeah, I think he has it mute. I think it should be okay.
Okay. All right. So this one is my explanation about previous question. So assuming to n larger than one, so the term, this term has order of one. Okay, so we get the on complexity because this is n in like in the previous explanation over here. Okay, nice. Okay, so instead of writing it like T1, T2, T3, I will write it in the O1 only because we have the complexity of this line is O1. The complexity of the smaller one here is O1 also, and this one also they have the complexity is O1. So I can rewrite the time function like instead of T1, T2, I can write O1 plus n. N is the size of the array you already know, multiplied by O1 plus O1. And because n multiplied by O1 over here is a term which has the highest order. So this is the On complexity.
So is it a fixed function that we need to use every time for calculating big O? Or?
No, it's not a fixed function. This is the time function. I interpret it in the easiest way to understand.
Okay.
Okay, right. Previously, we have this is like the time because this is the time over here. But now I just define the time. We have defined the time to the O1 because the complexity of this line of code is O1. And the complexity of this line of code also O1 and similarly O1 and can write into this form. Is it good?
Yes. Yes.
Okay. Nice. Right. This is my explanation to the work one example. So why they say that you remember? I hope you remember. I say O1 equal to ON equal to O2N equal to N but plus one. Remember that?
Yes.
Okay, nice. I have to go back to this. So please, we have the previous example, but we have another follow-up over here. The Indians of this one must not be here, but it should be the same to the previous Indians. Delete this one. Okay. So right finishing the follow-up over here, we have another follow-up. So you must not be confused because these are not two follow-up. The second follow-up is not inside the first follow-up, but they are two distinguished follow-up. Okay. Is it good?
What is distinguished follow?
Like tức là cái dòng for này nó sẽ được làm sau khi mà cái này nó dạy xong rồi.
Ok, chị hiểu rồi.
Chứ không phải là cái for này nằm ở trong đây anh chị.
Ok. Đây là nó là 2 lần n hả?
Dạ đúng rồi. Dạ đúng rồi, đây là cái mà em muốn nói. Dạ. Đây là cái nó nói, ví dụ như T này mình sẽ có là O1 nha, là O1 chỗ này.
Ok.
Chắc là mới bấm cái gì nó ngu rồi. Rồi tức là cái dòng for loop, tức là mình sẽ có cái O1 là cái O1 này cộng cho n lần cái O1 này cộng cho n lần cái O1 này cộng cho cái O1 này. Thì em có phải viết ngắn lại rằng nó sẽ là hai lần nhân n nhân với O1. Xin lỗi các em nhầm, tức là 2 cộng với 2 lần O1 này. Mà thì nó sẽ là O2n, bởi vì cái hai term của mình ở đây là 2n. Nhưng mà mình cũng có thể viết lại như sau, là cái t cũng như ở trên luôn, từ đây viết xuống là 2n nhân cho O1 cộng cho 2 lần O1 cộng cho 2 lần O1 thì nó sẽ bằng n nhân cho cái cụm này. Mình có thể coi cái này là hằng số, thì khi mà mình coi cái này là hằng số á, cái này là biến á, thì nó chỉ là on thôi. Thì đây là lý giải một cách ngắn gọn đơn giản là tại sao mà O2n bằng với lại on. Em phải là bằng mà là nó tương đương nhau, giống như là O1 nó sẽ tương đương với lại O2. Thế là chị hiểu không chị? Dạ luôn.
Chị quên mất unmute. Smith, do you got it? Smith, you got it, like why on is equal to O2n? Từ từ nha, để chị ngắm cái này coi, chị chưa hiểu lắm.
Dạ, cái đoạn này đúng không chị? Cái đoạn này nó hơi khó hiểu nè.
Chị chưa hiểu sao on bằng
em nói lại lần nữa nha, hơi chậm nha. Là cái chữ cái t á, cái hàng mà phức tạp của mình á, bây giờ em sẽ viết thêm lại theo kiểu là O1 nè cộng với n nhân với O1 là tại vì cái này thực hiện n lần, cộng với n nhân với O1 tức là cái này thực hiện n lần, cộng với O1 ở đây tức là cái này thực hiện một lần. Thì tức là thằng này nó sẽ là 2n là gom thằng này với thằng này lại. NO1 cộng NO1 tức là 2NO1 cộng cho 2 nhân với O1. 2 nhân với O1 này tức là 2 cái O1 này. Thì cái 2N này á, cái term này nè, cái term 2N nhân với O1 này nè, nó có cái order, tức là nó có cái order chỗ này là 2N, thì kết quả của mình là O2N là cái độ phức tạp của nó.
Ok. Tại vì nếu mà n bằng 1 thì nhân với cái gì trước nó cũng bằng 1 lại, đúng không em?
N bằng 1. N ở đây thì là một cái số nào đó bất kỳ mà mình không được nghĩ nó là cái số cụ thể.
Okay.
Mà mình không được nghĩ nó là cái số tự nhiên nào đó cụ thể, nhưng mà mình phải nghĩ nó là một số bất kỳ. Thì ở dưới đây em có thể viết lại theo dạng là n nhân cho O1 nhân 2. Nhưng mà khi viết cái dạng này á, thì nó lại có cái độ phức tạp là ON. Trong khi cái T này là 1 thì mình có thể nói rằng cái O2N này nó tương tự như là cái ON.
Ok.
Mình cũng có thể áp dụng cái cách suy nghĩ đó tương tự với cái việc là O1 với lại O2 và O3, O4, 5 vân vân.
chị hiểu rồi. Ok, Smith,
Yeah.
đúng là nắm rồi. Chắc mình qua slide tiếp.
Yeah. Thì nó gọi là sao ta, nó không phải là cái kiểu toán mà nó hơi rõ ràng á, tại vì nó liên quan tới một phần nữa phức tạp lắm, em nghĩ là không nên hiểu nhiều về nó, nên là giải thích theo kiểu này.
Ok.
Dạ. Phải nói tiếng Việt luôn hả chị, để cho
Thôi nói tiếng Anh lại đi chứ không Smith nó complain. Smith nghe được. Okay, back to English.
Okay, so let's go for O and power 2. Yeah, I guess you are familiar with this kind of matrix, right? We have the list in the list. We have the list here inside the bigger list over here. See, you see that the first list, the second list, and the third list, and three of them is inside the list empty. All right. So the question is, ignore any function in NumPy or any function from Python, any helper function. I want to calculate the sum of the sum of each element in the matrix. So you have any idea to do it?
Like find the big O complexity, right?
Yes, but before we talk about the big O complexity, my question is just how can I find the sum of all element in the matrix over here?
Yeah, I'm not sure without using libraries like pandas.
Yes, this is the problem, because when we come to the algorithm, we have to have a way, when to have method before using the given function, right? So my idea is about using for loops, and the first loop is something you can go from row to row, and the second loop is you can go for column to columns. I guess we already talked about the two ways to calculate the sum of the matrix in last 3 lectures. You remember it? And this in that day I already talked about it, and now I repeat. Okay. All right. I will do this function. I guess that I have the example code in the folder material I already gave you yesterday, today, and this is how I can do the code. I call the summing to function. We have the first for loop. Why in the array? Array here means empty, and we have empty over here. Okay, I in the array means I will be the list, this list, this list, and this list in the order of appearance. Like in the first iteration, I will be 10, 22, 1. In the second iteration, I will be 41, 11, and 12. And in the last iteration, I will be 13, 41, and 11. Okay. Okay. So for J in I means J will be 10, will be 21 and 1. In the next iteration, J will be this one, this one, this one. and we have the total. Total means summing. Will be the accumulate value of j, like 10 plus this one plus this one plus this one, and so on. All right, this one has the complexity of O1, this line has the complexity of O1, and this has the complexity of O1. So before we go on, can you tell me, are you confusing about this level?
No, I'm good. I think I'm good. I think we studied 2 weeks ago. So
Yes, nice. So can you okay, we go on by filling in the time function over here. So for, I think for saving time, I will do it for you, so we can saving time for the recursive part. Basically, this one will be because this one will be called n time, which n is dimension of the matrix. I mean, if you have the matrix over here and you have n element, I mean n and columns and rows, right? So it will be the dimension of the matrix. Like say mình duyệt cái gì? Mình duyệt cái ma trận này theo chiều dọc, rồi theo tầm mỗi lần ở cái row này thì mình sẽ duyệt nó theo chiều ngang. Thì after on we will have the n time of this iteration and n times of this iteration. Okay, so because we have n here and n here, we will got n multiplied by n multiplied by O1. Previous example, we have just one for loops, so we just have one n. Now inside the for loop, we have another for loop. So it must be n multiplied by n. Right, we have the O1 over here, O1 over here, and in the end of the day we have n power of 2, so the complexity is O n power of 2.
so the complexity of ON could be equal to ON square root 2, right? No, not square root power 2.
No, actually it's not equal, because you remember that in the previous example over right here we just have one iteration only. In the next example we have 2 different iterations.
Oh, okay.
And this example we have the iteration inside the iteration. I mean the for loop inside the for loop. Right, so we have n multiplied by n time, so n square, and because n square is the highest order in the time function, the complexity function, so we got the complexity is O n square. Is it good?
Sorry, I forgot to unmute. So the n square is because you call the element twice, right?
Not twice. What I can say is in each calling in each calling line here, I will call it again.
Oh, so the element change twice, so that's why it's n square, right?
Actually, when we said about twice, we said n multiplied by n, right? But in this case, it's not. It's the n multiplied by n.
Yes. So because the element in the array here, it transformed twice, so n times n, so that's why it n power 2, right?
Yes, we have you have the matrix over here, right? So with the matrix the matrix has n rows. The matrix also has n columns. For example, we have to how to say that in English, mà mình muốn duyệt một cái ma trận thì mình bắt buộc phải duyệt từng phần tử của nó bằng cách là mình dùng hai cái vòng lặp như thế này. Là tại cái vòng lặp thứ nhất ý là cái vòng lặp bên ngoài thì mình duyệt theo cái hướng dọc xuống, là mình có thể làm ngược lại, nhưng mà trong trường hợp này là mình duyệt theo cái số dòng của ma trận. Thì trong ví dụ này lần duyệt dòng đầu tiên nó sẽ có ba lần duyệt cột nữa, tức là mình có 3 lần duyệt dòng và 3 lần duyệt cột. Tức là tại một lần duyệt dòng này mình bắt buộc phải duyệt cái cột 3 cột này. Và tại lần này sẽ làm cái này và tương tự, thì tức là mình sẽ có 3 x 3 là 9 lần duyệt.
Ok. Tại vì hai số 3 lặp lại nên nó là n mũ 2 đúng không?
Dạ, thì có thể như vậy.
Okay, yes, I got it.
We got n multiplied by n, so mean O n square complex. Nice.
Yes.
So make sure that you understand this one, because it's kind of important, right? If you please, if after this tutor, if you're not clear about it, we can discuss it in chat, on message, or I can give you simple, much more similar example on how we can execute it in Python.
Okay, I think I'm clear.
Okay, good. So before we go to the log n, I want to kind of review the logarithm mathematics. All right, so actually it should be a log of 2. We say this is the base. Sorry, the base. And how this one perform, it could be 2 power of 3 is 8, right? So the log 2 of 8 must be, can you guess number?
Log 2 of 8, 4, right?
No,
two.
This is the, actually
3.
the number in between. Yes.
I just reviewed the good math yesterday and I forgot already. It's 3, okay.
It's okay, because like is the one is the inverse of the power. This one is the inverse of the power. 2 power of something equal that number. So log 2 of this number is equal to something. All right, so we have some small example. Can you guess what is number over here?
Oh, so we would need to find. Oh, because yesterday I think.
You just think about it. 2 power of something equal for 16.
4.
Yes, exactly. Exactly. So a little bit difficult. No, I gave you an answer. 67.
Yeah,
All right.
I wouldn't know how to calculate it.
All right.
Yeah.
So this is a little bit back to the logarithm and just talk about the binary search.
Mm-hmm.
I guess you already have an idea about it. You have the array,
Mm-hmm.
you divide it into two parts. You
Yes.
compare a number that you want to, assuming this array is already sorted.
Mm-hmm.
You want to find the number n, and you
Mm-hmm.
compare the number n with the middle, right? If n smaller than the middle, you will divide this in the first part one into
Mm-hmm.
three, and you compare it again. If n is bigger than the number, you divide this one again and again, right?
Mm-hmm.
So just think about it. The worst case, you will divide the array is the number. That's the result is a log of two.
Mm-hmm.
To be more specific, like let's say um, you want to check that the number 5 is in the array of 1, 2, 3, 4, 5, uh, um, 5, 6, 7 to 10, right? At
Mm-hmm.
the first time, you are very lucky, right? Because we already know 5 is in between. You divide into two parts and you compare to the middle, right? So
Mm-hmm.
5 is right in between of the array. So I'm lucky we can know that this one is in the array. Yes, and we exit. But in the worst case, like we want to check uh, what number? Let me think.
Mm-hmm.
Uh, from 1 to to 8, and we want to check number. For example, we don't know that the number 3 kind of weird, but we don't know the number 3 in the array of from 1 to 8, and we
Mm-hmm.
want to look for the number 3 over here, and we have to divide into two parts.
Mm-hmm.
You know, 4, right? 4 is smaller than this one, have divided again, and we got number 2 over here, and still larger than this one, and we have to divide it again, and we got the 3 over here,
Mm-hmm.
right? So this takes 3 times to divide the array.
Mm-hmm.
Am I right?
Mm-hmm. Yes.
Okay, to check the number 3 is in the array or not.
Mm-hmm.
Similarly, if you have the 14 element array, you have, in the worst case, you have to divide to 4 times.
Mm-hmm.
So you see the correlating between the length of the number and the worst time, the worst case that you have to divide the array is log 2 of size of the array,
Mm-hmm.
right? So we call this the O log n complexity,
Mm-hmm.
right? So I think it's clearer when we put the number, the base of 2 over here, so
Mm-hmm.
we can understand it in using the binary search
Mm-hmm.
algorithm.
Yes.
Yes. So this is the easiest example that I can think in my head to describe about the O log n.
Mm-hmm.
Actually, we can find another like uh, algorithm which perform the O two, even 3 or 4 or something. But at the moment I cannot find the those algorithm, and
Mm-hmm.
because stick to basic examples. Okay.
Yeah, sure.
Okay. So summing up, on is something relating to one, say, the for loop, right? One iteration.
Mm-hmm.
Log n is something relating to the binary search. This
Mm-hmm.
one is any stupid function that just take one time to execute whatever the input is, right?
Mm-hmm.
On power of 2 is the iteration inside the iteration.
Mm-hmm.
So can you guess what is? Just give me a example in on power 3.
Yeah, so basically it would be like the number, for example, like if you have a number that it would have to transform 3 times. Right. So
Uh,
for x in the this for x in the array and for e in x and for y in e. So something like that.
yes, but we can think it in iteration again, but we have three iteration inside of each other, right?
Yes.
Iteration inside of iteration inside of iteration.
Mm-hmm. Mm-hmm.
All
Yes.
right. So I guess you have there's something. I hope that you have something clearer about the
Mm-hmm.
ON complexity.
Mm-hmm.
Okay.
So,
All right.
so for example, like if we have like for e in enumerate, like the enumerate last time at
Yeah.
me. So for e in enumerate, that it would be like O and 3, right?
ON only.
Oh, but then enumerate is that mean like if you have the array, then you transform it twice. Not twice, but like, you know, according to the array number is.
The yes. So we see ONN, right?
Oh, but in
Because we don't know the size of the array we transform.
oh, that's right. Yes.
Yeah, yeah,
Yes. So we need to know the data input.
yes,
Oh, okay. Yes, I think.
yeah. All right. So this will give you the idea of the any function, any line of code, or any algorithm. We will it will execute how much time will consume, and just think about it before calling it, because sometimes we will take a lot of time on it, right?
Mm-hmm.
Okay.
Mm-hmm. Yes.
Uh, so you need a break, or we'll just go to the
No,
recursion.
we can do go to recursion.
Okay, 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 right. Right. Um, we already know that recursion is a function called itself. Remember,
Mm-hmm.
and the recursive function need to stop, and the condition is given base case. And like I said in the last time, is where you can exist is the condition we can exist the loop, the infinite loop,
Mm-hmm.
right? And which put down this one, the program we want forever.
Mm-hmm.
Uh, I guess Python will give the warning. I'm not sure about the yes, Python will give you the warning when it doesn't have the base case, or just you can see the just see when the terminal run forever, or it doesn't display anything for a long time. You know that your program is stuck in the infinite loop. Um, the recursion use stack memory architecture for storing current variables. So this is the stack. The stack mean something go in the last will go out in the first.
Mm-hmm.
Let's see it in like this. Um, the action of give something in is pushing, and the action of take someone out is hopping. And see this is the memory or something go into the stack at very first, and it have to wait until another variable popping, and this one could be popped in last. Is it good?
Yes.
Yeah, so this is the idea of stack memory.
Mm-hmm.
All right. Yes, like I said, that to understand the recursion, the good way is tracking or tracing each line of code. So let me go with you through two, three, actually four example, but the last example take a lot of time. So I think this would be nice for homework, right?
Yes.
Okay. I will go example by example, and the first one will be the summing recursion. The idea and the problem is how can we calculate the sum from 0 to given number? To be more specific, how can we calculate the sum from 0, for example, given number 4, calculate 0 plus 1 2 plus 3 plus 4. You have any idea on doing it?
You use like the factorial formulation. Would you do it?
Factorial is something about the multiplication. But
Oh,
now
so
just yeah. It's also okay, but this is just symbol in summing only. You have any idea for doing this?
Oh, we can write a function for that. So
Yes.
so we can like for e in length like 0 and the length of array, then just sum it.
No, actually we don't have any array here. We just have a number only. Don't be we don't try to complicate in the problem. Just a number only. We don't need the array because it will waste the memory.
Yeah, I'm not sure how to do it.
Okay, no problem. I will go into this problem. So let me share on my screen. Okay, can you see my not plus?
Yes.
Okay, this is the purpose. I mean the final target, but we don't focus on this now. I will write another function like symbol summing of a here or e in range a. I have to total equals 0 for e in range a total plus equal y. Actually, range a plus 1. Return total. Now we call the bring symbol function of tree. Um, all right, so I'm running my example again. This is my Python folder. and this is a Python when you call it for execution the Python, and this is the name of this example is file recurve sum, right? So and I run it, and we have the result, which the input is 3, so which means 0 plus 0 plus 1 plus 2 plus 3 equals 6, right? Okay. So this is a simple example on summing. Are you okay with this?
Yes.
Okay, I guess so. Instead of using the for loop over here, I can do the recursion function. How do I do it? It's easy. Just have a look on this. And like I said in the slide, we have to trace line by line, right? So actually, some Python IDE provide you the tool for debugging the Python, but I forget how to use it in Python. If we use the Python debugging tool, we can run the Python code line by line, and you can see how the program is executed. But in back to our example over here, when we call the bring summing recursion of 5, the program will jump into the line of 2 and check whether the I mean 5 here equals 0 or not. If not, it will return the A plus summing recursion of A minus 1. All right, so how to do it, because I plan on using the tripod for showing my written note, but actually I forget my tripod in company today, so I cannot set up this kind of play, so I will do it in the next lecture
Yeah.
for
Oh, Vũ,
introduction to table.
maybe we can split it and we have like another lecture next time. So we can have your function. We can leave the recursion section to next time, and we can talk about recursion in the next session. With
It's okay. Are you busy now or something?
no. I just wonder like if we can see it better in the with a tripod, and we can do it next time also.
Yeah. Okay.
Up to
Okay,
you.
but yeah, it's okay. But let me finish this example.
Okay. Sure.
All right. So instead of using the handwritten, I will write right here, right in the
Okay.
part over here. Let's imagine the stack equal something, right? I have it here. So you remember my slide about the stack, right? The first in and will be the last in out. Okay.
Yes.
So right at the moment you call the summing recursion a minus 1, you have the variable a, I mean the number 5. Still nothing to do with it, right? We have nothing to do with the number 5 at the moment. And you input the 5 here. We'll check. Oh, one more thing before we go on. Whenever the function is called, any variable inside the function will be erased by the memory right after you call the return. For example, I declare a function total equal to 0 here, right? So right after the return total here, and the total variable will okay, it will be erased from the memory. Even I or even I or A over here, all nothing will be erased for freeing the memory. But thing will be different in the recursion. You call the return over here and you call the recursion. It will not be erased yet and it will be stored in the stack. See, if it's here number 5, number 5 will be here if it is in input of this one number 5, this number 5, and the number 5 will be stored in the stack right after you call the summing this recursion. Okay.
Yes.
And okay, let's continue, and when we call the a minus 1, right now a here mean a here mean 4, right? Okay, at the first calling, first call a equal to 3, right? At the second call a equal to, can you guess? This one minus 1 is 4. Okay, actually recursion. Are you good? I mean right after running this one, right after running the return a plus this one, and the stack will be 5. The number 5 will be stored in the stack, and like this one, like you call the recursion 5, and you call the recursion a minus 1, mean you call the recursion of 4. Okay.
Yes.
Okay.
Yeah,
Nice.
I understand how it works.
Yeah. Nice. And it check 4 is not 0. 4 is not 0, so it doesn't return anything. It return the 4. I mean, yeah, 4 plus this one, and right as you call this one, the number 4 will be stored in the stack. Oh, by the way, this in and no, not the end, not good word. But this notation. All right. So similarly, it would be 3, 2, 1, and 0. No, not 0 here. At the first, it should be 4. At the 4, it could be 2. At the 5th, a will be 1. And right at the moment you call summing 1 minus 1, 1 will be stored in the stack, and you call 1 minus 1 mean you call the summing recursion of 0. You call the summing recursion of 0. A equal to 0, and it check a equal to 0, right? It check a equal to 0, and it return 0. So it returns 0 mean we will have the result of 0 over here, and it take back the stack to this line. right at the moment, it returned by calling a equal to 0 over here. It should be the time for return for exiting the recursion. So by the way of exiting the recursion, it will call the number one. It put into here, put into this position, this place of code, and no summing something, and it delete it from the stack, and it do the addition. And similarly, we will do the exit take 2 from the stack, take 3, take 4, and take 5 from the stack, and do the excursion. For better understanding, I will add my 2 lines of code like over here. Bring A is no in the R0. No, it's not good. A star. Okay. And okay, it's not good a good place for bringing this. Let me think. All right. Can you are you clear at the sixth time the recursion is called and the a equals 0? Are you with me at this point?
Yes.
Okay. So right at this one, you see the 0 and the recursion, the sixth recursion exists. The sixth recursion is raised, and the number 0 will be input here. A number of 0 will be input here, and the a will be 1 because previously we have 1, 2, 3, 4, 5 in the stack. Oh, we should change the code. We have to write it next to it, like return 1 plus 0. 1, 2, 3, 4, 5. All right. Right at the moment a equal to 0, it will return 0. Mean it that in the sixth recursion it will be 0, and the a is it take back from the stack and it delete it from the stack. Are you clear with me? Are you with me?
Yeah, I think I understand this function.
Let me check. All right. I just keep in mind that we have to return it back, and by continuing this example, I will take this example. It is in nothing but just bringing out the value. Which is bringing out the value from, we have a function SR. We have a function SR here, and it does nothing but just bring out the value of A. You see? And when we call the SR of 5, and this function check the A, I mean, check the file. If file smaller than 1, it will return, and this is my base case. And if a equal or greater than 1, it will call the recursion of a minus 1. Check. Okay, and let me run this code, and it's easy to trace back. So are you seeing my output of the program here? Recur 1.py, recur 1.py, and when I call the SR5, the function will bring bring file and the text right after that. When just enter the SR function, and you see file, when just enter the SR function, okay, and it run the next line, a smaller than 1 in return, and if not, it will, I forget to demonstrate the stack equal something here. Right after we call the SRA minus 1, the value of a mean 5 is stored in the stack, 5 over here, right? And we call SRA minus 1 mean we call SR of 4, and the program will bring out the line 4 when just enter the SR function, 4 when just enter the SR function. Okay, and 4 is still greater than 1, so it doesn't return, and it will call the SR of 3. Similarly, we have here, oh, I forget to put it into the stack 4 here, because right after calling the recursion, you would have the number of the variable will be stored in the stack like this. Okay, and similarly, we have the 3. We have the 2, 1, and 0. Because 0 is smaller than 1, it will return. It will return. And we have number 3 over here. 3, 2, 1, because we have the stack, and I did not update the stack during calling SRA minus 1. And you see, this is the place where the stack is popping here, right? When it return in this line, it will continue what would it have to be done before going to the SRA minus 1. Here, it will bring a when just get out from the previous recursion. It means 1, because 1 here is the number 1 in the stack, and because this is the value of a, and I already said that a is stored in the stack. All right, so it deleted from the stack. See the value of 2 over here, and it return, and this line will be called. This line will be called, and a here A2 because A is the value popping out the stack, right? Again and again and again. When nothing else is in the stack, and the recursion will be uh, finished. The recursion will be finished. And you see in the last element, I mean number 5, the first thing you remember in the first line of code, the number 5 is something going to the stack firstly, and this will get out of the stack lastly. Number 5. I guess it's little difficult to understand.
No, I think I understand. Actually, by the way, we use FIFO and LIFO in the financial too. So yeah, I understand that concept.
Yes, but I guess a little confused on why is go back to here and bring this one. I guess, right?
No, I think
Uh,
it's the same. Yeah, I think I understand.
yes, but just let's see the text I bring out right after the number.
Sure.
Yeah. Um, this is like say the nailing point, so we can see what the program is doing, and this is my example to understand it. So I guess if you are clear at this point, we can go back to this example. All right. So similarly to that previous example, when we call this one into the stack like this, and it will be calling back over here, right? The sixth recursion, the A must be 0, remember? So this one returns 0, this is 0, and this one will be popping out the stack A, and 1 plus this one equal to 1, right? One of this one equal to 1, and what does it return? It returns the 1 to this place, equal 1 here, and 1 here is 1 here. 1 here is 1, and it returns the normal 1 in the stack, and it returns 2. Stack 2 here and 2 here. Right, and again, and the result is 3 plus 3 plus 3 plus 4 plus 5. So at the end of the day, you will have the summing from 1 to the n, to the number n.
Yes, I think I understand.
Okay, because it's a little bit complicated, so I guess
Alright, I
this
think
is better for you to recheck the function here again, and also the summing recursion again before we go on of next two example of exponential and Fibonacci in the next lectures. Okay.
Yes. Yeah, I think I understand. Don't worry.
All right. So, any question so far?
No, I think I'm good. Do you have questions, Smith? Yeah, I think he's good also.
Okay. Okay, so if you don't have any question, and I will stop it, and then next time I will review it the example again, and continue with next two examples.
Sure. Sure. See you next time. Thank you for today's meeting.
Yeah. Thank you.
Okay, thank you. Yeah, thank you, Smith, for attending.